There we go. So if we just got two position graphs and no time graph, we can't directly figure out the period, but we can certainly measure the wavelength. Wavelength is just going to be distance from crest to crest or trough to trough. So let's say here's a crest, here's a crest. So this distance from 4 to 10 is definitely one wavelength. So we can say wavelength is that distance. 4 to 10 is 6, so wavelength equals 6 meters. I'm just going to assume these distances are in meters. So we know the wavelength. Amplitude, the y values aren't actually marked here, so we're just going to treat a as some constant that we don't care about the value of. But we've got the wavelength. We can fill that in. Wavelength 6 meters. And the period we can't directly measure from the graph, but how can we find the period anyway?
Frequency times wavelength.
Yeah, frequency times wavelength should equal what?
The speed.
Yeah, frequency times wavelength. Yeah. Don't need the whole thing, just frequency times wavelength equals speed. And we know the speed that's given. We know the wavelength that's measured from the graph. So frequency equals speed over wavelength, which is going to be 2 meters per second divided by 6 meters. In other words, 1/3 hertz. And then how would you convert that to period?
It would just be 1/1/3, so 3.
Yeah, 1 over the frequency is 3 seconds. So we can fill that in as well. Period is 3 seconds. By the way, that term 2 pi t over the period, sometimes it's more useful to write that 2 pi t over period. Dividing by period is the same as multiplying by frequency. So sometimes it's easier to write it as 2 pi times the frequency times the time instead of 2 pi times the time divided by the period. Same thing, just a different way of writing it that's sometimes more useful. So it looks like we know the period, we know the wavelength. We're still missing the phase shift, the little phi constant, which we would usually find as a very last step. And we still need to find the direction of travel also to figure out the plus or minus. So for direction of travel, if we had an x graph and a t graph, we'd be looking for a point in common. 1 point on the x graph and 1 point on the t graph that have the same coordinates. For instance, this top x graph is at t equals 6 seconds. So we look for t equals 6 seconds on the other graph. But in this case, the other graph doesn't have t equals 6 seconds. It's an x graph, shows all x values, but only shows one time value, 10 seconds. And since the 6 seconds and the 10 seconds don't match, there is no point in common here. So instead, we're going to have to use a different approach. And what I would generally do in a case like this, if you've got 2 position graphs or 2 time graphs, look for let's say a crest on one graph and a crest on the other graph that represent the same crest as it moves, or a trough on each graph that represents the same trough as it moves.
I have a question.
Yeah.
So about that, since it's like a sinusoidal graph, how would we be able to know that the same like peak or trough is the same peak or trough as the bottom one?
This is actually why, this is the reason ultimately why we need to be given the speed. If we didn't already have the speed, there would be no way we could tell. Without the speed, we might be thinking, well, maybe this crest moves, because it looks like this is 4 seconds passing from time 6 seconds. At time 6 seconds, the wave looks like this. At time 10 seconds, 4 seconds later, the wave looks like this. So maybe over the course of those 4 seconds, this crest moves from x equals 10 to x equals 6. Or maybe this crest moves from x equals 10 to the right to x equals 12. Or maybe it moves really far to the left, all the way from x equals 10 to x equals 0. Or maybe this trough at x equals 7 moves to the right and gets to x equals 15. We don't know which crest matches which crest or which trough matches which trough. We know it's moving, but we don't know which direction or how far. But if we have the speed, we can tell how far. Because how is speed defined? What is speed? When we talk about speed, what does that actually mean?
It'd be like distance over time, right?
Exactly, distance over time. Well, the period and velocity are related to the wavelength or frequency, or the wavelength. But the fact that we have the velocity and how much time passes is really the important thing. That we know that from the first graph to the second graph, that represents, and if you think of this as a snapshot, the X versus Y graph is a snapshot or like a photograph or a still image of the shape of the wave at that instant in time. Like if this is waves on a rope, this graph literally just represents the shape of the rope at that instant in time. If you imagine you've got a video of the wave passing through the rope and you press pause, this is the shape of the rope at that single frame still image. And we know that we're looking at two snapshots taken 4 seconds apart from each other. So that 4 seconds is delta t. We also know the speed that was given as 2 meters per second. So we can solve for what else? Yeah, solve for delta x just by, in this case, just by multiplying both sides by time. So the distance traveled during those 4 seconds is going to be the speed times the amount of time, or 4 seconds. So that'll be 8 meters. So that means we don't know yet which direction this wave is traveling, but we know during this amount of time, the wave moves 8 meters. So we should be looking for a crest on one graph and a crest on the other graph that's exactly 8 meters apart. Or a trough on one graph and another trough that's exactly 8 meters apart. And so what I would usually do there is choose a crest or a trough near the center of one of the graphs. Let's say, for instance, maybe we could take a look at, here's a trough that's near the center. Here. That trough at 7, during those 4 seconds, that trough could move 8 meters to the right or 8 meters to the left. 8 meters to the right would put it at what location? Yeah, that would put it at 15. So maybe this moves 8 meters to the right and ends up at x equals 15. That's one possibility. Or maybe it moves, because we don't know the direction of travel yet, maybe that crest or that trough moves 8 meters to the left and ends up where? If you start at 7 and you move 8 meters to the left, yeah, you end up at exactly -1. So that's another possibility. And we don't know yet which one of those it is. You can't tell just from looking at this one graph. So maybe this ends up at x equals -1. To figure out which one it actually is, we compare this to the other graph. We take a look at the locations x equals -1 on the other graph and x equals 15 on the other graph. Does it look like either of those locations have a trough? Yeah, it looks like 15 is definitely a trough. -1 is not exactly on the shown on the graph here, but you could certainly imagine continuing to draw this. If you just continue this, it looks like, I'm guessing that would probably hit equilibrium at -1 or somewhere near equilibrium. Probably not quite to equilibrium because the wavelength is 6, so it's not actually going to hit equilibrium, but definitely not a trough. But there is clearly a trough at x equals 15. So what we can conclude then, since we know that the wave travels 8 meters, and this is a trough that is 8 meters away from this trough, we can now, we can ignore these stuff to the left. And we can say that this moving 8 meters to the right is what really happens, because we know that at time 6, there's a trough at 7 meters. We know that in the next 4 seconds, that trough has to move 8 meters. And oh, look, here's another trough that's exactly 8 meters away. So that means these two troughs are really the same trough. That is, this trough has moved 8 meters to the right to get from x equals 7 to x equals 15 during those 4 seconds. So I think we can say that this wave is moving to the right. Any questions on that so far?
So this is how we would find the direction, right?
Yeah, I would say so.
Okay, and then find naught, we would just like plug in the other values, right?
Yeah, once you know the direction, that tells you, since it's moving to the right, we'd use minus in the plus or minus. And at that point, we now know everything about the phase, the total phase, the stuff inside the sine function, except for phi naught, the phase shift. So for that, you could just pick any location on either graph, ideally a crest or trough, plug in the coordinates for x and t. And if you've got a crest, you'd set the total phase equal to pi over 2. If you got a trough, you'd set the total phase equal to 3 pi over 2. And then you can solve for the phase shift. Any other questions on that so far? One other thing on direction, if you got 2 x graphs, then I guess it's a little more intuitive once you've chosen the same crest on each graph or same trough on each graph to see, oh, it's moving to the right, or oh, it's moving to the left. But it's not always visually obvious, especially if you're dealing with 2 time graphs instead. If you're dealing with 2 time graphs, you'd be using mostly the same procedure. It's just that you'd have an x value for one of them and an x value for the other. So you'd know delta x, and you'd instead be solving for delta t to figure out how far into the future or how far into the past is the same crest on the other graph or same trough on the other graph. But in both cases, what I would recommend, if it's not visually obvious which direction it's traveling, draw out an x-axis and mark the 2 locations on the x-axis. Like in this case, we know that this trough hits x equals 7, and on the other time, this trough hits x equals 15. So if we mark x equals 7 and x equals 15 on the number line, so if we just place some marks on the number line here, x equals 7, x equals 15, and we know that a trough hits x equals 7, and that same trough hits x equals 15. Which one does it hit first, though? Does it get to x equals 7 or x equals 15 at an earlier time? Yeah, x equals 7. The trough hits x equals 7 at time 6 seconds. That's an earlier time. So what we can say is that this trough hits x equals 7 earlier, and the same trough hits x equals 15 later. So going from 7 to 15, from 7 at the earlier time, and then reaches 15 at a later time, that means it is moving in the positive x direction, moving to the right. And this approach, drawing out an x-axis and just marking the 2 points you care about, and asking yourself, which one of these does it hit earlier, which one of these does it hit later, That approach will work whether you're dealing with two x graphs or two time graphs, as long as you've got the x values of this trough or crest and the times that it hits it. Just comparing which one does it hit first, which one does it hit second. Any questions on that approach? All right, let's take a look at those other questions you sent me. What was that? Chloe, you were asking about question 3 on this practice quiz. So what are we trying to do here? Listen to music. We've got a background sound from both speakers, and we know the wavelength. And we want to know where in the room you won't be able to hear that 4 meter frequency or 4 meter wavelength. So we want to know, are there any locations in this room where you can sit and not hear the sound? And it looks like there's possibly several locations we want to consider. So what has to be true in order to not hear this sound at all?
Needs to be destructive.
Yeah, if you want to make sure you won't be able to hear the sound, that means we want destructive interference. So what has to be true in order to get destructive interference? How can we guarantee that? Yeah, we can set the phase constant, or not the phase constant, but the total phase. Because remember, the phase constant, the plus little phi in the equation, that's more to do with, in this case, whether the speakers are wired the same or wired oppositely. And this problem doesn't really specify anything about that. I think we'd have to, since it doesn't say anything about how the speakers are wired, I think I would just assume they're wired the same. Because I don't think it really gives us enough information to be able to tell. But I would just assume that they, oh, actually, yeah, it does tell us. Assume both speakers are wired the same way. They're in phase with each other. So that means there is no delta phase shift. We know delta little phi is 0. So we can say there's no phase shift difference because they're wired the same way. They are in phase with each other. Which means if you're standing somewhere in the room, what's the only difference between the two waves? Yeah, the only difference is the distance, x, how far they travel. And so we can actually use a simplified version of the total phase concept. Typically, we'd say that the delta total phase, let me actually pull up the variables for that. Total phase, there we go. Typically, we would say that the total phase difference looks like this: 2 pi t times difference in frequency minus 2 pi times difference in x over wavelength plus delta phase shift. But we know these two waves are in phase, so we can ignore delta phase shift. There is no difference in phase shift because they're in phase. Also, we know that the two speakers are playing the same pitch, the same sound, so there's no difference in frequency. The only difference we have to care about is this 2 pi delta x over lambda. So this simplifies greatly. We can say this is just 2 pi times, also the wavelength is the same, so we can factor that out. We just have delta x over lambda. There's no phase shift difference. And since we specifically want destructive interference, what can we set delta total phase equal to?
We would say pi.
Yeah, pi is one possibility, although what else could it be? Yeah, any odd multiple of pi. And what's the usual mathematical way of writing out odd multiples of pi? Or just odd numbers in general?
We do the 2n plus 1.
Exactly, 2n plus 1. So this is our simplified version of the total phase idea. If the only difference is path length, there's no difference in frequency, no difference in phase shift. So all that's left is the 2 pi delta x over lambda. And we can ignore the negative sign here because it doesn't really matter if the odd number is a positive odd number or a negative odd number. So if you've only got one term, it doesn't really matter if it's positive or negative. If you're dealing with two terms, like if there was also a difference in phase shift, then you would want to consider the sign on this, positive versus negative, because it matters. It makes a difference if you're adding things or subtracting things. But if there's only one thing in the entire equation, it doesn't really matter if it's positive or negative. Also, what else can we simplify now? What shows up on both sides of the equation here? Yeah, pi shows up on both sides, so we can divide both sides by pi, cancel that out, and now we get an even simpler equation. Looks like this reduces to just 2 over lambda times delta x equals an odd number, 2n plus 1. Also, we should probably be careful about this x here because we're using x as the horizontal coordinate as opposed to y for the vertical coordinate. We probably want to write this then not as x, but as r. R is what we usually use for radial distance. So we're just going to use r here to represent the diagonal distance traveled by the wave. And there is a difference in how far the wave travels. That's the delta r we're talking about. We could then also solve for delta r, multiply both sides by lambda over 2 to cancel out the 2 over lambda. We get 2n plus 1 over 2 times lambda. In other words, if we simplify a little bit more, 2n plus 1 over 2 just becomes n plus 1/2 wavelengths. So in general, if you're standing at a location where the difference in path length is 1.5 wavelengths, then you get destructive interference. And I think that fits in nicely with the general idea of destructive interference being 1.5 cycles offset. And cycles can be more complicated than just wavelengths because there might be more differences. But in this case, the only difference is path length. So destructive interference means the path length difference is 1.5 wavelengths. Any questions on the algebra there so far? So, and we know the wavelength, right? 4 meters. So if we fill that in, we get n plus 1/2 times 4 meters. Distribute the 4, we get 4 meters times n plus half of 4 meters would be 2 meters. So what we're looking for is locations where the difference in path length is 2 meters plus or minus some multiple of 4 meters. So let's try that. Actually, before we look at the actual locations, we might want to look at just some possible values of delta r. For instance, what's probably the easiest number we could plug in for n? Even easier than 1? Yeah, let's try 0. When n is 0, you plug in 0 for n, you just get 2 meters plus 0. So it could be 0 meters. Or no, not 0, we still have 2. So if one of the waves travels exactly 2 meters longer than the other, then we get destructive interference. Or if we do go ahead and plug in 1, delta R would be 2 meters plus an extra 4 meters, so that'd be 6 meters. Or if n is 2, 2 meters plus 2 times 4 meters would be 10 meters. Or if n is 3, difference would be 2 meters plus 3 times 4, so that would be 14 meters. So it looks like every 2 meters and every 4 meters beyond that, 2, 2 plus 4, 2 plus 4 plus another 4 plus another 4, all of those delta R values will lead to destructive interference. So that's what we want to look for. If we can find locations where delta R is 2 meters or 6 meters or 10 meters or 14 meters and so on, those would be locations where we find destructive interference, quiet zones. Any questions on that so far? So let's find those locations. If we were just arbitrarily looking for this entire space in the room, we might set up an equation and figure out what zones are going to be destructive. But in this case, we just need to look at these 4 possibilities. We've got some locations marked 1, 4, 2, 4, 0, 1, and 3, 1. Looks like those are already marked here. Yeah, 0, 1, 1, 4, 2, 4, and 3, 1. Mark 3, 1 also. So for these locations, we've got 4 locations we want to check here. And what we care about is the actual delta x. Or sorry, delta r, because we care about the difference in path length. So for instance, I think these ones on the same y value as the speakers are going to be easiest. If we just take a look at the distances there, we've got distance traveled by one of the waves and distance traveled by the other wave. What can you say about how far? That's not a good color for that. Let me make this a little more visible. Maybe, no, still not a good color. Are any of these colors going to be visible? How about that? If we got those 2 paths, what can you say about the distances traveled by those 2 paths? From speaker 1 to this location versus from speaker 2 to this location. Yeah, it's exactly the same distance. One of them is traveling 2 meters. The other one's also traveling 2 meters. So since they're the same distance, same path length, so delta R is 0 meters. What sort of interference would that provide if there's no difference in path length? Right, that's going to be constructive interference. If you're standing at this location, 2, 4, you're going to hear a very loud sound. And that's not what we want. We don't want a loud sound. We want everything to cancel out. So this is not going to be a good location to stand. Instead, let's try another location. If we try the location 1, 4, now those waves are traveling different distances. It looks like the left speaker, the wave only has to travel 1 meter. The right speaker, the wave has to travel 3 meters. What's the difference between those path lengths? Yeah, the difference is 2 meters. And it looks like that's on our list. 2 meters is one of the values that causes destructive interference. Exactly. This 2 meter difference. And note that the actual distances traveled don't matter. All that matters is the difference between how far they travel. Since the difference between the distances is 2 meters, and that's on our list, that means that is a value that leads to, that is a location that leads to destructive interference. So it looks like that is exactly, or one of the locations we're looking for. This is destructive interference. And now let's take a look at the other locations. Let's say 0, 1. If we got a wave from speaker 1 to this location and from speaker 2 to this location, how far is the wave from speaker 1 traveling to get to this location? Yeah, just traveling south 3 meters from 4 to 3 to 2 to 1. What about this other diagonal here? How would we find that distance?
We use Pythagorean theorem.
Yeah, Pythagorean theorem looks like that's 3 to the south, 4 to the west. So what would be the hypotenuse? Yeah, that's the standard 3, 4, 5 right triangle, or you could just actually calculate it out, 3 squared plus 4 squared, and you get 5 meters. So what's the difference between those path lengths? Yeah, 2 meters. And we already saw that a difference of 2 meters leads to destructive interference. So it looks like this location also fits the bill of destructive interference. So we currently have 2 locations that lead to destructive interference, which we want, and 1 location that leads to constructive interference, which we don't want. We still need to test this one other point though, so let's try that. Any other questions on this so far before we check the last point? Then for this last point, we have a wave from speaker 2 traveling to this location and a wave from speaker 1 traveling to this location. And again, we'll want to use Pythagorean theorem to calculate the distances. Looks like these won't be nice, neat whole numbers because we've got 3 to the south, 3 to the east. So 3 squared plus 3 squared equals r squared. That'll be 18, so square root of 18. That will probably actually on the calculator. Root of 18, 4.24-ish. So R1 is about 4.24 meters. And then R2, looks like we're going 3 to the south, 1 to the east. So 3 squared plus, or west. So 3 squared plus 1 squared, 10. So square root of 10 is 3.16. So what would the delta X or delta R be in that case? .08 meters. Would that lead to destructive interference? No, that is not fitting the description of 2 meters plus or minus a whole number times 4 meters. It's also not going to be constructive interference because it's not a nice, neat whole number of wavelengths. That's just going to be some sort of partial interference. So at this location, you'll hear some sound. It won't be very loud, but it will be there. And we don't want partial interference. We want destructive interference. So it looks like there's only 2 locations that will work, 1, 4, and 0, 1. Of that list anyway. There will be other locations elsewhere in the room that will also work, but from this list, those are the only ones that work. Any questions on that so far?
There was a same question or a similar question on the same quiz where they gave us like 2 different frequencies for the speakers and then like asked us where in the room like you wouldn't hear sound. Would you like approach that? Like, I guess, how would you approach that kind of problem?
In this case, you said the speakers are different frequencies?
Yeah, I can send you a picture of it.
In that case, with different frequencies, you're going to get beats as the main phenomenon. There won't, if the frequencies are different, you're not going to be able to find individual locations where it's constructive or destructive. It's going to be changing what type of interference as time passes. And that actually goes back to, if you go back to the original equation here, this one here, if the frequencies are different, that means there is a non-zero delta frequency, which means this term doesn't drop out. And if this term is still there, that means time actually matters. So the type of interference you get will change as time passes instead of just being the same at all times. So that's what leads to beats. If the frequencies are different, then you get a type of interference that changes as time passes.
Okay, so in that case, you would hear like some kind of beat wherever in the room you are. You couldn't hear like no sound.
Sorry, what was that?
So if it's like 2 different frequencies, that means, I guess, like wherever you go in the room, you would be hearing like some kind of interference. There wouldn't be a position where you would just hear like nothing.
Right, and then you're going to hear the type of interference rapidly changing as time passes, cycling back and forth between loud to quiet to loud to quiet to loud to quiet. Because as time passes, this value is going to be gradually increasing, and there will be some instance in time where it hits a whole number of cycles, then something and a half cycles, then the next whole number of cycles, then the next something and a half cycles. So as the time increases, the total value oscillates between whole number of cycles, something and a half cycles, whole number of cycles, something and a half cycles in terms of total delta phase. And that means it's going to be oscillating between loud and quiet and loud and quiet. And that oscillation between loud to quiet is what we call beats. And for that, I think the main things to know are that the idea of the carrier frequency, the average sound, the average pitch you actually hear, which is literally just the average of the 2 frequencies, add them up and divide by 2. That's called the carrier frequency, as opposed to the beat frequency, how many cycles of loud, quiet you hear per second. And that's equal to the difference in frequencies. Any other questions on that so far? All right, and you were asking about problem 1 on this practice quiz also. Let me pull that up. Yeah, it looks like this one is also talking about beat frequency because we're looking at 2 different frequencies here. And thus we hear this annoying beat frequency. The trumpets are not quite in tune. At a specific time, could you hear destructive interference? Yeah, for the whole idea of beats is that as time passes, you're oscillating between constructive and destructive. So there will be certain instance in time where it's completely destructive at that location, and certain instances where it's completely constructive. So we have 2 different frequencies, in this case, 2 different frequencies, but then one of the trumpets starts moving towards the listener while the other one remains still. And what's the condition on observed frequency for which the beat sound disappears? So what has to be true in order to not hear beats? Well, it's not about destructive versus constructive, because remember, beats is talking about alternating between constructive and destructive. With no beats, that doesn't mean it's destructive or constructive or partial. It just means that it's not changing as time passes. And yeah, one way to put this is we want the beat frequency to be 0. We want no loud, quiet oscillations per second. We don't want any beats at all. But what does that tell you about the two frequencies you're hearing? You would hear beats in the first place because the two trumpets are out of tune. They're providing different frequencies. So what has to be true in order to not hear beats at all? Yeah, you've got to be hearing the same frequency from both of them. Now, of course, these trumpets are not producing the same frequency. The two trumpets individually are still out of tune. But why would you hear the same frequency even though they're not producing the same frequency? Yeah, the Doppler effect. And again, this one is not about where you stand. The where you are doesn't really matter in this case. The beats are not caused by where you stand. Beats are caused by the frequencies being different. We want the frequencies to be the same, not the produced frequencies, but the frequencies you actually hear. And Doppler effect is about a change in what you hear as a result of what? What causes Doppler effect? What has to be happening? Yeah, movement of source or observer. And it looks like in this case, I think the listener is staying still. It doesn't, yeah, the listener is just sitting there. The trumpeter playing F1 is marching towards the listener. So that means frequency 1 is going to be modified, or rather the observed frequency is modified. So that means the observed frequency is not going to equal F1. But the other trumpet is still staying still. So F2 does not change.
Sorry, can you repeat why the observed frequency doesn't equal F1?
Sorry, what was that?
Could you repeat why the observed frequency isn't equal to F1?
Yeah, the fact that the source is moving. In general, if the source is moving or the listener is moving, then the Doppler effect is going to be in play here. That the frequency that the listener hears is not the same as the frequency that the source produces. Because if you imagine the source is moving very fast, then the wavefronts it's creating in front get bunched close together because the source is moving forward. The wavefronts coming out the back get more spread out because the source has moved. So the motion of the source means that the observer is hearing a frequency that's different from the frequency that the source is producing. The observed frequency is not the same as the produced frequency if the source or the listener is moving. But since trumpet 2 is staying still, that means frequency 2 is heard exactly as it was produced. We don't have to worry about Doppler effect for frequency 2 because source 2 is not moving. I think we can ignore then any options that claim that F observed equals F1 because we know frequency 1 is modified by the Doppler effect. So it looks like the first option claims frequency observed is the same as F1, and so does the third option, so we can ignore those. The second option I think is kind of misleading here because it's claiming that the observed frequency is the average of the frequencies. But the thing is, we know that the F2 is not changing. So F2 stays exactly as it is. What we want, in order for the beats to disappear, we need the observed frequencies to be the same. But we know F2 stays the same. So we just need the observed frequency of the first one to match F2. So it looks like that's this fourth option here, that the observed frequency, and I think that's supposed to be, that should really be marked as the observed frequency from source 1, has to match the frequency that you're hearing from source 2. That would imply that the two sounds you're hearing have the same frequency, thanks to the Doppler effect. And so that means you don't notice any beats. Any other questions on that? You're welcome. All right, looks like that's it for now. I will see you next time.
Thank you.
You're welcome.